Okay guys, I fixed, I hope, all my issues. Well, not my issues, but issues of this setup. I replaced the sensor. So what I'm showing you right now is just pure water. Nothing added to it yet. Just water. So when you look at your data sheet, there will be an entry there. It says beaker with pure water, and theoretical pH would of course be 7. And for measured pH, take a look here. I have about 6.78. So a little bit on the acidic side, which is not uncommon for DI water, for the reasons of how it's being prepared from tap water. So really close to pH of 7. So this time we're going to take a look at what happens in the buffer and water when we add strong base to it. So once again, this is my water to start, about 6.7 or so, although now it's for some reason reading lower. But in this beaker here I have my original buffer, my other half of the buffer. So I'm going to use the electrode. And remember, the expected pH of that buffer was 4.75, and we once again are seeing 4.59 and 4.6, so fairly close to the expected value. So I'm going to take this buffer beaker and this water beaker, 25 milliliters of buffer in this one, 25 milliliters of water in this one, same volumes, different solutions. I'm going to set them right here. And in this bottle here I have 6 molar sodium hydroxide. So next we're going to add 0.5 milliliters of 6 molar sodium hydroxide to each beaker containing buffer and water, and we're going to then measure the pH. So once again, this is a 5 milliliter pipette. I'm going to fill it up to 0 with 6 molar NaOH, and then 0.5 milliliters of 6 molar NaOH is going to go into each of these two beakers. First into buffer, and now into water for a total of 1 milliliter. 0.5 milliliters into each. I'm going to use my stirring rod to stir. And now we can go ahead and measure our pH. We're going to start with buffer. So now we took our original buffer that had pH of about 4.6, measured. And now this buffer has base in it. So pH did go up, but as you can see, it didn't go up by very much. It's now reading 4.7, so it started with about 4.6 or so, and now it's up to 4.7. So obviously we're adding base, so pH has nowhere to go but up, and it did go up, as you can see. And now this is water with added base. And look at this. So water started at around 7, a little bit on the acidic side, and now with only 0.5 milliliters of added NaOH, pH for the water went all the way up to 11.78 or even 11.80 or so. So huge increase in pH in water, compared to the buffer. So how do we explain this? Let's take a look. So what did we do? We took 25 milliliters of our buffer and we added to it 0.5 milliliters of 6 molar NaOH. So moles of NaOH are equal to moles of hydroxide ion, which is 0.005 liters times 6 moles per liter. That gives us 0.003 moles of hydroxide. So we're adding hydroxide. We have to make a decision as to what the hydroxide that we're adding is going to react with in our buffer. Again, we must make a choice. Remember, buffer contains two components, acetic acid and sodium acetate. In this case, only acetic acid can react with hydroxide. Hydroxide cannot react with acetate. Acetate is a base, and acetate has negative charge, just like hydroxide does, so they can't even approach each other in solution. So the only possibility here for our reactant, in this case, would be the acetic acid in the buffer. So acetic acid in the buffer is going to be reacting with hydroxide. A here stands for acid, B stands for base. Remember Bronsted theory, acid donates a proton to the base. So proton is moving from acetic acid to hydroxide. What would the products be? Well, if we take H away from acetic acid, we're going to get acetate ion, and the second product that comes from combining hydroxide and H plus from acetic acid would be water. Again, you see the red arrows. So what are those arrows representing? They're representing expected changes in concentration of buffer components. So acid in the buffer is going to decrease in this instance because acetic acid is a reactant when NaOH is added. Concentration of acetate, on the other hand, would be expected to increase because acetate would be produced in the reaction. It's a product. So ice table numerically looks exactly like the first one we looked at. Again, we're starting in our original buffer with 0.012 moles each of acetic acid and acetate. Remember, both acetate and acetic acid are present in the buffer, and 0.012 moles is half of 0.024 moles that we originally put in our buffer when we first made it. So what are we adding? We're adding 0.003 moles of hydroxide ion that came from 0.5 milliliters of 6 molar NaOH. So as soon as we add this amount, the concentration of acetic acid is going to decrease by that amount because all of the hydroxide is going to be consumed in the reaction. So the concentration of hydroxide in the end was going to go down to 0. All of the hydroxide we added is going to be used up. So how much acetic acid is going to remain? Well, 0.012 minus 0.003 gives us 0.009 moles of acetic acid remaining. What about acetate? Well, acetate is now a product, so we started with 0.012 moles of it. In the reaction, we produced extra 0.003 moles of it, so the total amount now is 0.015 moles. So how does our Henderson-Hasselbalch then change? Well, now the concentration of base in the buffer is greater than that of the acid. So basically the larger number, 0.015, goes on top because that's the acetate concentration. And the smaller number, 0.009, that's the concentration of remaining acetic acid, and that's going to go to the bottom. And if you do the math, what you will see is that this pH, theoretical pH of the buffer with added base, should be something close to 4.9. We didn't quite get that for our measurement because my pH meter was acting up, but we did get an increase in pH in the buffer with added base versus original buffer. So here the expected pH is going to be about 4.9. Last thing I'm going to discuss real quick is how do we find the pH of water with added pure water, right? Obviously assuming it's dry water. Expected pH would be 7. Our measured was about 6.7 or so, or 6.9, I don't remember, but hopefully you wrote it down. So now we are adding, we take 25 milliliters of H2O, and we're adding 0.5 milliliters of 6 molar HCl, right? And we have to find pH of that solution. And to find the pH, we would have to first find hydronium ion concentration. So all this is simple dilution. Strong acid diluted with water. So we can use our dilution formula, which we haven't talked about in a while, to do this calculation. So M2 would be equal to hydronium ion concentration in our water with added HCl. So we can put M1 V1 divided by V2. M1 would be 6 molar because that's the concentration of acid we started with. How much acid did we add? We added 0.5 milliliters. Now what is V2? Let's think about this. We started with 25 milliliters of water and we added 0.5 milliliters of 6 molar HCl. So total volume would be the sum of these two, 25.5 milliliters. So what you're going to do is you're going to find hydronium ion concentration first for water with added HCl, and then once you have hydronium ion, you're going to use it to find pH. Hopefully you know how to do that. Remember, if you have hydronium ion, you can take negative log of that number and that will give you the pH. What about when we took 25 milliliters of water in the other beaker and added 0.5 milliliters of 6 molar NaOH to it? Well, similar calculation. The only difference is when we are doing our M2 calculation, we're actually finding concentration of hydroxide because obviously NaOH is a strong base and will completely dissociate, producing hydroxide ion. The numbers remain the same. We took 6 molar NaOH, we added 0.5 milliliters of it, and our total volume was the sum, which is 25.5 milliliters. So we have M2 here, and that's OH. So how do we get to hydronium ion? So we find hydroxide first, and then hydronium ion can be found as Kw divided by hydroxide concentration, right? Kw is 1 times 10 to negative 14th, and then you're going to divide it by hydroxide concentration, and it's going to give you hydronium ion, and then from there you can find pH. Or what you could also do here is find OH concentration, and then find POH, and then pH. Remember, POH plus pH is equal to 14. And then you could find hydronium ion this way. So finding hydronium ion this way or this way is the same, meaning you're gonna have you're gonna get the same answer. Point is, in this case, your pH is going to be very, very high because your concentration of hydronium ion is so low because concentration of hydroxide is high. Here, on the other hand, because we're adding acid, your pH is going to be very low and your concentration of hydronium ion is going to be very high. So point is, here in water, unlike in the buffer, there is no mechanism for resisting pH. So as soon as you add either strong acid or strong base to the water, pH in this case is going to decrease dramatically to about 1. In this case, pH is going to increase dramatically to about 13, I believe, if you do the calculation, or 12, something like that. We measured 11, so it was definitely very high. I hope this helps you. with filling out your data sheet. When working on the data sheet with pHs of water and the buffer, my recommendation is do them separately. Do all the buffer beakers first and then do all the water beakers first, because calculations are so different. That's all.